Chapter 4. The Periodic Table of the Elements. The atomic structure of the periodic table of the elements according to the Yaldon model. This will be a brief discussion about the shape of the atoms according to the periodic table of elements without going into detail on the nature of the forces applied on and by the atoms. The shape of the hydrogen atom is similar to the shape of a galaxy, disc-like with a dense mass in the center. The dense mass in the center of the hydrogen atom will spin rapidly about its axis, and the Yaldon particles that surround it will whirl about the dense core, creating a disc-like shape. The conservation of momentum in the universe will maintain a steady amount of Yaldon particles that move around the dense spinning core. When there is a steady amount of Yaldon particles around the core, then this will be known as a neutral element, neutron. Should there be a shortage of Yaldons around the dense core, then that atom will be positive. This is due to the movement of the Yaldon particles toward the spinning dense core. If there is an extra amount of Yaldons around the spinning core, then the conservation of momentum in the universe will move the extra Yaldon particles away from the spinning dense core. When the extra Yaldons move away from the dense core, this atom will appear to have a negative charge, since the spinning dense core of mass, without the Yaldons spinning around it, appears to be positively charged. Then this rapidly spinning dense core of mass will be called a proton. Following will be figure 4.1 representing a galactic model for the hydrogen atom. Kinetic disk of Yaldons around the proton in the center. Figure 4.1. A rough diagram representing the galactic model of a hydrogen atom. This will be the basic building block for the rest of the elements. The next element in the periodic table is helium. Helium will consist of a central shaft of two hydrogen atoms that are stacked on top of each other with a short distance between the two atoms, not touching each other, and another two hydrogen atoms which revolve on a plane perpendicular to the central shaft, forming orbit A. The central shaft of hydrogen atoms will create a suction force perpendicular to its axis of rotation. The central shaft of hydrogen atoms will create a suction force perpendicular to its axis of rotation. The central shaft, along with the two orbiting atoms, will create a gyroscopic model. The central shaft can be considered as a nucleus of an atom. The rest of the elements in the periodic table will also be gyroscopic. Following will be figure 4.2, which will model this concept. Central shaft of hydrogen atoms, nucleus. Figure 4.2. A rough diagram representing the gyroscopic model of a helium atom with two hydrogen atoms that fill orbit A. The next atom on the periodic table of elements is lithium. Lithium will require a new orbit. Orbit B. Following will be figure 4.3, which will model the lithium atom and orbit B. Figure 4.3. A rough diagram representing the model of a lithium atom with four hydrogen atoms in the central shaft. There will be two hydrogen atoms in orbit A and one in orbit B. The newly added orbit B will be able to hold another 7 hydrogen atoms. This will be able to fulfill the second row of the periodic table of elements up to neon. The central shaft, nucleus of the atom, will continue to collect hydrogen atoms until the neon atom will have 10 hydrogen atoms in its nucleus. The neon atom will also have 2 hydrogen atoms in its inner orbit, orbit A, and 8 hydrogen atoms in its outer orbit, orbit B. Following will be a rough diagram representing the general shape of a neon atom, figure 4.4. Nucleus shaft consisting of 10 hydrogen atoms. Orbit B has 8 hydrogen atoms. Orbit A has 2 hydrogen atoms. Figure 4.4. A rough diagram representing the shape of a neon atom. For the atoms in the third row of the periodic table of elements from sodium, Na, to argon, Ar, they will form another orbit, orbit B', parallel to orbit B. Orbit B' will be able to have another 8 hydrogen atoms in its orbit, and this will be able to fulfill the periodic table of elements from the sodium atom to the argon atom. The nucleus shaft will also continue to stack hydrogen atoms onto it, growing in height as the atoms grow heavier. The force of the nucleus shaft that is perpendicular to the axis of rotation in the direction towards the nucleus will also increase as the nucleus's height increases. Following will be figure 4.5, modeling the general shape of an argon atom. Argon, Ar. Nucleus shaft consisting of hydrogen atoms. Orbit B has 8 hydrogen atoms. Orbit B' has 8 hydrogen atoms. Figure 4.5, a rough diagram representing the shape of an argon atom. The atoms in the fourth row of the periodic table of elements from potassium, K, to krypton, Kr, will form a new ring from orbit C. Orbit C can hold a maximum number of 18 hydrogen atoms in its orbital path. Following will be figure 4.6, modeling the shape of the atoms from potassium to krypton in the periodic table of elements. Orbit C, orbit B, orbit A,
orbit B'.
Figure 4.6, a rough diagram representing the shape of the atoms in the periodic table of elements from potassium, K, to krypton, Kr. The growing nucleus shaft will have a range of 20 to 48 hydrogen atoms within it, from potassium to krypton. The atoms in the fifth row of the periodic table of elements, from rubidium, Rb, to xenon, Xe, will form a fifth orbital ring, orbit C', that can also hold 18 hydrogen atoms and will be parallel to orbit C. See the following figure 4.7. Figure 4.7, a rough diagram representing the shape of the atoms in the periodic table of elements from rubidium, Rb, to xenon, Xe.
The growing nucleus shaft will have a range of 48 to 77
hydrogen atoms within it, from rubidium to xenon. The atoms cesium, Cs, barium, Ba, and laphthanum, La, will have hydrogen atoms that occupy a sixth orbit, orbit C'. The first 6 atoms in the lanthanide series, from cerium, Ce, to europium, Eu, will expand orbit A. The path of orbit A will increase in size and hold 6 more hydrogen atoms for a total of 8 hydrogen atoms in its orbit. The name of orbit A will change to orbit B' after the increase in size. The rest of the atoms in the lanthanide series from gadolinium, Gd, to lutetium, Lu, will form stacks of 2 hydrogen atoms in orbit B', for a total of 16 hydrogen atoms, 8 stacks of 2 hydrogen atoms. The following atoms in row 6 of the periodic table of elements, from hafnium, Hf, to radon, Rn, will fill orbit C'. And add another 15 hydrogen atoms to this orbit, 18 total hydrogen atoms in orbit C', for radon. Following will be figure 4.8, which will show the general shape of the atoms in row 6 of the periodic table of elements. In figure 4.8, the bold line for the orbit path of orbit B', presents the stack of 2 hydrogen atoms that occupy that path. Figure 4.8, a rough diagram representing the shape of the atoms of the periodic table of elements from cesium, Cs, to radon, Rn. The growing nucleus shaft will have a range of 78 to 136 hydrogen atoms within it from cesium to radon. The atoms in the 7th row of the periodic table of elements, from francium, Fr, to rutherfordium, Rf, and including all of the atoms in the actinide series, will form stacks of 2 hydrogen atoms in orbit C'. Figure 4.9 will be a rough diagram modeling this concept with a bold line for orbit C'. Figure 4.9, a rough diagram representing the shape of the atoms in the periodic table of elements from francium, Fr, to rutherfordium, Rf. The growing nucleus shaft will have a range of 136 to 157 hydrogen atoms within it, from francium to rutherfordium. The rest of the synthetic elements in the 7th row of the periodic table of elements, starting from dubnium, Db, will form stacks of 2 hydrogen atoms in orbit B', B', C, or C'. In this way, the atomic model of the periodic table of elements can be fulfilled with a gyrocentric model of a central rotating shaft with orbital rings that form a well-distributed area for the mass contained within the atom. This model of Yaldon particles was developed since, according to Newton's second law of motion, Ft equals mv, there cannot be momentum, force, energy, or time without a mass in a bounded system with relative motion to other points of reference in that system. All of the above formulas, discussions, and diagrams are used to implement this principle on the atomic scale of the universe without having to rely on an alternate reality. The term Yaldon was chosen for the assumed particle since the root of the word Yalda is translated into winter solstice from Aramaic. The winter solstice marks the first day of the year when the daylight begins to become longer, and these Yaldons are responsible for light. Hopefully, this model will be used to help humanity further understand the world and the universe within which it resides, in order to develop helpful tools and devices to promote a harmonious world for all.